students. In this video, we are going to learn about heterocyclic compounds. Before going to heterocyclic compounds, we must know about homocyclic compounds. Homocyclic compounds are the compounds which contain the atoms of the same element while forming the ring. That means in the ring, all the atoms present belongs to the same element only. For example, benzene. Benzene contains 6 carbon atoms in the ring. All the 6 carbon atoms belongs to one element only. Likewise, toluene and cyclohexanol. On the other hand, heterocyclic compounds. These are the compounds contain atoms of two different elements bonded to each other while forming a ring. That means in case of heterocyclic compound, the ring contains at least two different elements. Generally, carbon is the one element and the other elements are heteroatoms like nitrogen, oxygen, sulfur, etc. For example, go through the following examples. Pyrrole. Pyrrole is a heterocyclic compound which contains 5 atoms like this, 4 carbon atoms and 1 nitrogen atom. Here nitrogen is the heteroatom present in addition to the 4 carbon atoms. It is in heterocyclic compounds. Furan is another example which contains oxygen as the extra element heteroatom present in addition to the carbon atoms. These are the 4 carbon atoms. It's a 5-membered heterocyclic compound. And thiophene, it is also a 5-membered heterocyclic compound. It contains sulfur as a heteroatom extra element present in addition to carbon, 4 carbons. And pyridine is a 6-membered heterocyclic compound in which nitrogen is the extra element. It is a heteroatom in addition to the 5 carbon atoms present in the ring. These are all the examples of heterocyclic compounds. The common heteroatoms present in the carbon ring, as we also already seen, are oxygen, nitrogen, sulfur. Actually, these compounds, they may be aromatic or may not be. And generally, they are 5 or 6-membered compounds. What we have already seen is pyrrole is a 5-membered heterocyclic compound. Furan, thiophene, they are 5-membered heterocyclic compounds. Whereas pyridine is a 6-membered heterocyclic compound. And they are very stable and possess certain amount of aromatic properties, and they are mostly abundant in plant and animal products. Now we are going to learn in detail about pyrrole. Pyrrole, its aromaticity, its structure, preparation, properties, etc. We are going to learn now. Pyrrole is a 5-membered heterocyclic compound which contains 4 carbon atoms like this and 1 nitrogen atom. All these 5 elements, 4 carbons and 1 nitrogen, they undergo sp2 hybridization. All are sp2 hybridized. That means each carbon atom, that means 4 carbon atoms and 1 nitrogen each contain 3 sp2 hybrid orbitals and 1 unhybridized orbital like this. Each carbon atoms contains 3 sp2 hybrid orbitals and 1 unhybridized p orbitals. Each sp2 hybrid orbital of an atom overlaps with the neighboring carbon atom or nitrogen atom to form a sigma bond. And the third sp2 hybrid orbital overlaps with s orbital of hydrogen to form a sigma bond. Likewise, all the carbon atoms they overlap with neighboring atoms and with hydrogen to form sigma bonds. And we are now left with one unhybridized p orbital on each carbon atom and like this, and one unhybridized p orbital on nitrogen atom. All the unhybridized orbitals present on the carbon atom contain a single electron, unpaired electron, while the unhybridized p orbital present on the nitrogen contain a lone pair of electrons. The adjacent the p orbitals present on the adjacent carbon atom, they overlap with each other sidewise to form a pi bond, like this pi bond. And these two p orbital overlap sidewise to form another pi bond. So we have two pi bonds and one lone pair of electrons. All these make 6 pi electrons forming an aromatic sextet. So it is aromatic. The compound is aromatic according to Huckel's 4n plus 2 pi rule. According to Huckel's 4n plus 2 pi rule, where n is equal to number of rings, here the number of rings are 1 only. Therefore 4 into 1 plus 2 pi, that means it must contain 6 pi electrons according to Huckel's rule. So pyrrole contains 2 pi plus 2 pi and these 2 electrons making 6 pi electrons. The compound is planar. Why? Because it is sp2 hybridized and it contains conjugation. So all the three aspects are satisfied by the pyrrole: planarity, conjugation, presence of conjugation, and presence of aromatic sextet to become an aromatic compound. So pyrrole is aromatic. Even though pyrrole contains double bonds, it won't undergo addition reaction. Rather than it participates electrophilic substitution reactions. Why? Because if pyrrole undergoes or participates in addition reaction, it loses its conjugation and loses its aromaticity. So pyrrole undergoes electrophilic substitution rather than addition reactions. If we see, these are the 5 resonance structures of pyrrole. This is pyrrole. The pi bond shifts like this, forming negative charge here. Automatically the lone pair of electron and the plus present here forms a double bond. Again this shifts, negative, double bond. Again this shifts, giving the final structure. So the resonance stabilization energy of this pyrrole is 21 kilocalories per mole, which is less than the resonance stabilization energy of benzene, which is 36 kilocalories per mole. Lower the resonance energy, lesser will be its aromatic character. That means pyrrole is less aromatic than benzene. Coming to preparations of pyrrole, pyrrole can best prepared by one method known as Paul-Nahr synthesis. One of the most important method, Paul-Nahr synthesis. In this method, the pyrrole is prepared by heating the enol form of 1,4-dicarbonyl compound with ammonia at 130 degrees centigrade to give pyrrole or pyrrole derivatives. This is the 1,4-dicarbonyl compound. This is a carbonyl group 1, 2, 3, fourth position of carbonyl group. Fourth position contains carbonyl group. Therefore, is 1,4-dicarbonyl compound. For this carbon atom, this is the alpha position, and for this carbon, this is the alpha position. The alpha hydrogens present in this carbon atom will shift to oxygen to form an enolic compound. This is an enol, dienol. The enol form of this 1,4-dicarbonyl compound, when it is heated with ammonia, it loses 2 molecules of water to form pyrrole. And another method is succinamide. Succinamide, when it is heated with zinc dust, loses zinc oxide to form pyrrole. This is the structure of succinamide. When it is heated with zinc, it loses zinc oxide, 2 molecules of zinc oxide to give pyrrole. And the third method from furan. When a mixture of furan, ammonia and steam are passed over alumina Al2O3 at 500 degrees centigrade forms pyrrole. So furan reacts with ammonia when it is passed through alumina in addition with steam gives pyrrole. This is the third method of preparation. One is Palnar synthesis from the enol form of 1,4-dicarbonyl compound when it is heated with ammonia gives pyrrole. Another second method is from succinamide. When succinamide is distilled with zinc dust gives pyrrole by losing zinc oxide. And the third one is furan when it is heated with ammonia and steam at 500 degrees centigrade over alumina gives pyrrole. While coming to properties, pyrrole is a colorless liquid which boils at 131 degrees centigrade. Its boiling point is 131. Below 131 degrees 1 degree centigrade, it is a liquid, and above 131 degrees centigrade, it boils and becomes a vapor. And it is when it is exposed to air, it readily turns to brown, and it smells like that of chloroform. Its odor is like that of chloroform. And pyrrole is readily soluble in ethanol and ether, and it is partially or sparingly soluble in water. Chemical properties. First one is the acid character. Pyrrole is an amine. You know very well, it is the derivative of an amine, and it contains a lone pair of electrons. Even though it contains a lone pair of electrons, these lone pair of electrons participate in aromaticity resonance. That means these two electrons are part of aromatic sextet. So these two electrons are not readily available for donation. That is why pyrrole is a very weak base, whereas it reacts readily with strong bases like KOH to form salt. That means pyrrole is reacting with strong bases like KOH to form salt, means that pyrrole contains weakly acidic character. So it is weak acid. And coming to second important property, electrophilic substitution reactions. Just now we learned that pyrrole participate in substitution reactions rather than addition reactions. Why? Because if pyrrole participate in addition reactions, it will lose its conjugation and lose its aromatic character. That is why it undergoes substitution reactions. That too electrophilic substitution reactions. Why? Because the pyrrole molecule contains electron density above below the plane of the ring, so it undergoes electrophilic substitution reactions. If we observe the pyrrole, there are 4 carbon atoms. Here the nitrogen will be given 1, second, third, fourth and fifth position. This is the second carbon, third, fourth, fifth. Is C2 and C5 will have similar environment, whereas C3 and C4 will have similar environment. That means we have 2 different positions, C2 and C3. That means electrophilic substitution may occur at C2 or the electrophilic substitution may occur at C3 position. There are 2 chances. Which is favorable? That is the question now. If the electrophile attacks at its C2 position, that means the bond has to shift like this, so that the electrophile will attack. Negative charge will come here and electrophile will attack at this position like this. The pi bond will shift like this, positive charge here. This is the structure. This pi bond will shift like this, double bond, positive charge. The electrons, one pair of electrons will shift, double bond, positive charge. Finally, the hydrogen will be eliminated, giving the final structure, so that we have 3 resonance structures when the electrophile attacks at C2 position. And the another alternative, when the electrophile attacks at C3 position, C3 here. So this pi bond has to shift like this, negative charge, electrophile will attack here, positive charge will come here like this. Now next double bond will form here. So we have 2 resonance structures. In the previous classes we learned that the more the number of resonance structures, greater will be its stability. So the intermediate formed at C2 position will have more stability rather than the intermediate formed at while attacking at C3 position. That means when the electrophile attacks at a C2 position is favorable rather than when the electrophile attacks at a C3 position. So the preferable substitution of electrophile in case of pyrrole is C2. We can understand from this energy diagram. This is the pyrrole. This is the intermediate obtained when the electrophile attacks at C2 position, and this is the intermediate obtained when the electrophile attacks at the C3 position. This is the energy diagram. This is the energy. The intermediate obtained while when the electrophile attacks at C2 will have lower energy than the intermediate obtained when electrophile attacks at the C3 position. Lower energy intermediate will have more stability. This is favorable. So hence C2 is preferred over C3. So now we are going to see about different types of electrophilic substitution reactions. First one is halogenation. Pyrrole reacts vigorously with bromine and forms 2,3,4,5 tetrahydropyrrole. Pyrrole reacts directly with bromine. And the substitution occurs at all the 4 positions, second, third, fourth and fifth position, forming polyhalogenated product 2,3,4,5 tetrahydropyrrole. The second one is nitration. Pyrrole reacts with cold concentrated nitric acid in acetic anhydride to form 2-nitropyrrole. So pyrrole undergoes nitration. That means it reacts with nitric acid in presence of acetic anhydride at 5 degrees centigrade under cold conditions to form 2-nitropyrrole. Here the nitro NO2 plus is the electrophile and the substitution occurs at C2 position. We already learned that C2 is the preferable one. So it occurs at C2 position, 2-nitropyrrole will be obtained. The third one is sulfonation. Pyrrole reacts with sulfur trioxide in presence of pyridine to give 2-pyrrole sulfonic acid. Here the electrophile is SO3 and it preferably goes and attacks the C2 position to form pyrrole to sulfonic acid. The fourth one is Friedel-Crafts acylation or acetylation. Pyrrole reacts with acidic anhydride in presence of Lewis acid like SnCl4 at 250 degrees centigrade to give 2-acetyl pyrrole. Here the electrophile is CH3CO plus and it attacks at the C2 position here to give, here the electrophile is CH3CO plus. That means COCH3 will be the electrophile and attacks at the second position. COCH3, 2-acetyl pyrrole will be obtained. Fifth one, Raymer-Tiemann reaction. Pyrrole reacts with chloroform in presence of KOH to give 2-formyl pyrrole. So pyrrole reacts with chloroform similar to that of benzene in presence of a base like KOH to give 2-formyl pyrrole. At the second position, CHO group will be substituted to give 2-formyl pyrrole. Here dichlorocarbene is the intermediate. Next one is Kolbe-Schmidt carboxylation. Pyrrole, when it is heated with aqueous solution of potassium carbonate, gives pyrrole to carboxylic acid. The carboxylic acid will be substituted at the second position, C2 position, to give pyrrole to carboxylic acid. The next reaction is diazotization. Pyrrole reacts with benzene diazonium chloride, benzene diazonium C6H5N2Cl to give 2-phenyl azopyrrole. An azo compound will be obtained. Here it attacks at the second position, the hydrogen present in the C2 position and chlorine will be eliminated as HCl and a link will be formed, coupling will be formed between the pyrrole ring and the azo group to form 2-phenyl azopyrrole. Next major reaction is reduction. Pyrrole will be reduced to different products under different conditions. That means the product after reduction depends upon the reagents we use. Pyrrole, when it is reduced in presence of with zinc in presence of acetic acid, zinc and acetic acid at room temperature gives partial reduction and gives 2,5-dihydropyrrole. On the other hand, when pyrrole is reduced with platinum and hydrogen, that is catalytic reduction, gives pyrrolidine. Complete reduction or complete hydrogenation gives pyrrolidine. At two different conditions, two different products will be obtained. At room temperature, when it is reacted with zinc and acetic acid, gives 2,5-dihydropyrrole. When it is reduced with platinum and hydrogen, that is catalytic reduction, gives pyrrolidine. And finally, the oxidation. Pyrrole gets oxidized in presence of with chromium oxide and acetic acid to give meliamide. This is meliamide. So pyrrole on oxidation in presence of chromium and acetic acid gives a compound known as maleimide. So students, we learned about pyrrole, its structure, aromaticity, physical properties and chemical properties in this video. In the coming video, we learn about another heterocyclic compound, a 5-membered heterocyclic compound, furan.